So we've got a ton of fascinating material here on the Aurora Borealis, the northern lights,
Right.
ready to dive in and really figure out what makes this phenomenon so captivating.
Oh, absolutely. The aurora has been a source of wonder for as long as people have been around to see them. Even before the science was there, cultures all over the world were weaving the aurora into their myths and stories.
Yeah, I can see why, right? Imagine looking up and seeing these incredible shifting lights just dancing across the sky. I mean, without science to explain it, your mind's going to come up with something.
Exactly. I mean, take the Sami people of Northern Europe, for
Yeah.
instance. They have this term, guavsahas, which translates to, get this, the light you can hear.
Whoa, the light you can hear. So they actually attributed sound to this silent visual thing.
Precisely. Shows you just how deeply it fascinated them, that very human need to make sense of the unknown.
And it wasn't just the Sami either. The Mandan Indians over in North America, they believed those celestial lights were actually, get this, medicine men simmering their enemies in a giant celestial pot. Now, that's an image both kind of terrifying and totally captivating, but those early interpretations, as cool as they are, they couldn't have predicted the actual science behind the aurora, right?
Not a chance. It wasn't until 1619 that the big man himself, Galileo gave it the name we use today, Aurora Borealis, which means dawn of the north. But even he, with all his knowledge of the cosmos, didn't totally get what was really going on.
So what were some of those early scientific theories, and how did we get from there to what we understand now?
Well, you had some folks proposing things like reflected sunlight or even, believe it or not, distant fires as explanations. But as scientific tools got better, those ideas kind of fell apart. The real game changer, though, came from a Norwegian scientist named Christian Birkeland.
Oh yeah, Birkeland, I've come across his name before. What was it about his work that was so groundbreaking?
Birkeland, he was doing his thing in the late 19th, early 20th century, and let me tell you, this guy was way ahead of the game. He was obsessed with cathode rays and started to see a link between them and the aurora.
Now, for those of us who slept through physics, remind me what cathode rays are again, and how did Birkeland connect those to the northern lights?
All right, so think back to the old days of those bulky tube televisions, right? The images you saw on those screens were the result of cathode rays beams of electrons, basically striking a phosphorescent screen. Now, Birkeland, he was working with similar tech, and he had this wild idea. He theorized that the sun was shooting out charged particles, electrons mostly, and that these particles were interacting with the Earth's magnetic field, and bam, that's what was causing the aurora.
So he essentially saw a connection between those flickering TV screens and the shimmering aurora in the sky. That's some serious intuition.
No kidding, right? It was a radical idea for the time. And to prove it, he built this ingenious contraption called the Torella. Picture this, a miniature model of the Earth, sealed inside a vacuum chamber.
Ah, the Torella experiment. I've heard about this. It's like legendary in aurora research.
Totally. So Birkeland bombards his mini-Earth with these electrons, basically mimicking the solar wind. And guess what? He creates tiny auroras right there in his lab.
That's wild. He recreated this massive celestial phenomenon on a tiny scale. Talk about convincing evidence for his theory.
You'd think so, wouldn't you? He even went on to propose these electrical currents in the Earth's atmosphere, which we now call, you guessed it, Birkeland currents. But here's the kicker. His ideas were met with a lot of resistance from the scientific community back then. A lot of folks just couldn't accept that space wasn't a perfect vacuum, you see.
So what happened? How did Birkeland's ideas finally gain acceptance?
It's a bit of a tragic story, actually. Birkeland died in 1917. His idea is still largely unaccepted. However, and this is pretty amazing currents. However, decades later, long after he was gone, we launched satellites into space, and guess what they found? The solar wind, those charged particles from the sun, just as he predicted, and of course, Birkeland currents.
Wow, what a story. A reminder that even the most groundbreaking scientific discoveries can face pushback only to be proven right years later. But let's get into the actual mechanics here. We know the sun's a major player. So what's happening on the sun, and how does all that energy travel all the way to Earth to create these incredible light shows?
Okay, so the sun is this massive ball of energy, right? And it's constantly releasing this stream of charged particles, electrons, protons, the whole shebang, and this is what we call the solar wind. It's like a super powerful invisible wind just blasting through space.
And the solar wind, that's what interacts with Earth to make the aurora happen, but don't we have like a magnetic field around Earth? How does that play into it?
Right, you are. Earth's magnetic field, we call it the magnetosphere, it acts like this shield, deflecting most of the solar wind right around us. But, and this is key for the aurora, some of those charged particles, they get funneled in toward the Earth's poles, guided by, you guessed it, those magnetic field lines.
So it's like these magnetic field lines are these like cosmic highways channeling all these charged particles straight to the poles.
Perfect way to put it. And then when those particles, especially the electrons, when they collide with the atoms in the Earth's upper atmosphere, we're talking oxygen and nitrogen, that's when the light show really starts. That's your aurora.
Okay, so we have these like energized particles smashing into these gases in the atmosphere. How does that collision turn into those amazing colors we see in the sky?
Think of it this way. When those charged particles from the sun, they hit those oxygen and nitrogen atoms, right? They transfer energy, and those atoms get all excited.
Excited, like literally vibrating faster.
Basically, they jump up to a higher energy level. But atoms, they're kind of like us. They like to be chill, stable. So almost immediately, they release that extra energy they just got, and they release it, as you guessed it, light.
So the aurora is basically just excited atoms in the atmosphere calming down and giving off light. That's nuts. But why all the different colors? What makes some auroras green, some red, some even blue or purple?
Ah, the color depends on which gas is getting all excited and also the altitude where that collision happens and even how much energy is involved. So that classic aurora green, the most common one, that's oxygen atoms doing their thing at lower altitudes around 100 kilometers or so above
Okay,
us.
what about those amazing reds and purples you sometimes see? Is that oxygen too?
The reds, yeah, that can be oxygen, but way higher up, like 200 kilometers or more. But those blues and purples you mentioned, those are from ionized nitrogen molecules, and they hang out at a bunch of different altitudes.
Yeah.
It's pretty wild how those color changes actually tell us about what our atmosphere is made of at different heights.
It's like the aurora is this giant neon sign broadcasting the invisible recipe of our atmosphere. And speaking of variety, I mean, it's not just a static blob of color up there, right? It's all those amazing shapes, those rippling curtains of light, the arcs, those dancing beams. What causes all those dynamic formations?
Oh, those shapes, they're directly influenced by how much energy those incoming electrons have, how densely packed they are, even which way they're moving. Plus, of course, you've got the whole magnetic field lines thing, making it all even more complex and beautiful. The shape of the aurora often actually mirrors the shape of those invisible magnetic field lines.
Whoa. So the aurora isn't just this gorgeous spectacle, it's like a visual representation of the Earth's magnetic field, these forces we can't even see.
Exactly. When you see those curtains rippling, those arcs of light, it's almost like you're seeing a ghost image of Earth's magnetic field projected right onto the sky. And those dancing rays of light, those often pop up when the electron flow is super intense or if the magnetic field is getting extra wiggly.
That's amazing. And you mentioned earlier this whole question about sound and the aurora. People have been debating that one for ages, haven't they?
Oh, absolutely. So we know that sound, like the kind we usually think of, can't travel through the near vacuum of space where the aurora is actually happening, right?
Yeah.
But people have been reporting hearing sounds during auroras for centuries, especially the Sami. They describe crackling, hissing, whooshing, all sorts of things.
So, what's the verdict? Could those sounds actually be real, or are people just, maybe their senses are getting tricked by the visual spectacle?
It's a real head scratcher, and scientists are still trying to figure it out. Some theories suggest that maybe the electromagnetic waves created during the aurora, maybe they could interact with the Earth's atmosphere in a way that creates sound near the ground. But we need more research, that's for sure. It's one of those things we're still actively investigating.
And with all this talk about the magnetic North Pole shifting, does that mean the aurora will move too? Like, will the best places to see it change over time?
Yeah, that's a common question, especially with the news about the magnetic North Pole heading over toward Siberia. And look, it's definitely true that the magnetic poles, they do wander a bit.
Mm.
Over like really long periods, they even flip completely. But the link between the aurora and the magnetic field, it's complicated. The aurora isn't just going to like follow the pole on a map.
So those incredible displays we see in places like Alaska, Scandinavia, those aren't going to vanish overnight.
No way. The position and intensity, they might shift a little over very long periods, think thousands of years. But the basic science, that interaction between the solar wind and our magnetic field, that's not going anywhere. We can count on the aurora sticking around to dazzle us for a long, long time.
That's good to hear. But I have to imagine, even with all we know now, there are still things about the aurora that we don't fully understand, right? What are some of the big mysteries that scientists are still working on?
Yeah, there's got to be more to uncover. So what are some of those big aurora mysteries that scientists are still grappling with? Well, one of the big ones is just the sheer amount of energy involved. I mean, we're talking about these tiny electrons from the sun getting juiced up to insane speeds, but the exact way that happens is, well, it's still a bit of a puzzle.
Yeah, trying to figure out how a single particle gets that supercharged way out in space, that sounds crazy complicated.
It's a real challenge.
Yeah.
And speaking of intense, what about those sudden super bright auroras we sometimes see, the ones that happen during those geomagnetic storms? Talk about powerful and unpredictable.
Right. What's the deal with those?
Researchers are using some pretty incredible tools to study them, trying to figure out what sets them off, what's going on in those moments. There's these things, they're called ice cat radars up in Svalbard. Sounds like something out of Star Trek.
Ice cat radars. Okay, now you got to tell me more about that.
So IceCat, it stands for European Incoherent Scatter Scientific Association. Mouthful, right? But basically, these radars send out radio waves and then analyze how those waves bounce back from the atmosphere. It's like they give scientists this X-ray vision of the aurora, letting them measure stuff like density, temperature, even how fast those particles are moving, all in real time.
Wow, so it's like we can peek right into the heart of those collisions happening way up above us. That's incredible. And what about that observatory you mentioned, the K. Henderson Observatory? Why is that place so special for aurora research?
Oh, the K. Henderson Observatory, that's up in Svalbard too. Talk about a prime location deep inside the Arctic Circle, perfect for aurora spotting. And they've got it all up there. Specialized cameras, things called spectrometers that break the aurora's light down into different colors, magnetometers for measuring the magnetic field, basically everything you need to capture and study every little detail of those lights.
Sounds like the ultimate aurora chaser's dream destination. And speaking of chasing auroras, I bet our listeners are dying to know, how can they increase their chances of actually seeing this incredible phenomenon for themselves?
All right, so you want to become an aurora hunter. Rule number one, darkness is your friend. Get as far away from city lights as you can, national parks, remote areas. You know the drill. The darker the sky, the better your chances of seeing those subtle auroral glows.
So embrace the darkness. Got it. What about the best time of year to go aurora hunting?
Winter is your best bet. Long nights, that's what you want. And head north, as far north as you can, ideally above the Arctic Circle for the northern lights. Oh, and here's a pro tip. Pay attention to solar activity.
So, like, check the space weather forecast. Is that a real thing?
Oh yeah, it's absolutely a thing. You can find websites and even apps now that track solar activity, including these things called coronal mass ejections or CMEs. Basically, those are like bursts of solar wind that can trigger some truly mind-blowing auroral displays.
Got it. So if I see a CME on the forecast, book that flight north. Now, you mentioned before that photos sometimes make the aurora look even more colorful than it does to the naked eye. Why is that?
Ah, that's all about how our eyes work, especially in low light. Cameras, they're way more sensitive to light and color than our eyes are, especially in those dim conditions you get during an aurora. They can pick up on subtle shades and details that our eyes just miss.
So those jaw-dropping aurora photos we see online, they're not necessarily what we'd see ourselves.
Think of it this way. They're showing us a different side of the aurora, one our eyes aren't built to see completely. We've got these things in our eyes called rods and cones. Rods, they're great in low light, but they're not so good with color. Cones, on the other hand, they see color really well, but they need lots of light to work their magic. So during an aurora, our rods are going into overdrive, and that's why we might see more whites and grays than those vivid greens and reds.
So as amazing as those photos are, there's something extra special about experiencing the aurora in person. To be there under that sky, watching those lights dance, it just has to be incredible.
Absolutely. Nothing beats the real thing. It's a powerful reminder of how vast and dynamic our universe is, of the forces that are constantly at work all around us, even when we can't see them.
Well, we started this deep dive with ancient myths and stories, journeyed through some mind-blowing scientific discoveries, and ended up here in awe of this incredible dance of light and energy that is the Aurora Borealis.
And if there's one thing our listeners take away from all this, it's this. The next time you're under a dark, clear sky, remember to look up. You never know, the aurora just might be putting on a show just for you.